Hello.
Hello.
Hello. Hi.
How are
Hi.
you guys?
I'm good. Good.
You guys couldn't look any more alike. You look exactly the same. You guys staying busy with school?
Yeah. Yeah.
Yeah. What are you learning this week?
I'm learning the minus.
The minus. Ooh, the dreaded minus. So what's 2 apples minus 1 apple? If you had 2 apples and you take away 1, how many apples?
It's one. It's one.
1 apple. Yeah.
It's one apple.
Yep. I had an apple today.
Ooh, that's great.
It was good.
You're gonna be healthy.
Yeah, I'm gonna be healthy. That's what they say. An apple a day keeps the doctors away, I think is what the saying says. You eat an apple every day, you don't have to go to the doctor's office.
Okay.
It looks like you've lost a couple teeth there.
Yesterday I ate some apples.
You did?
Yeah.
Yep. That's why you don't have to go to the doctor today. You're nice and healthy. You should always eat apples. They're good.
Yeah.
So now you've learned the plus sign, the minus sign.
Yeah.
So now
Yeah.
you're ready to take your mom's classes for her. You can do her classes now and she can do your classes.
They're too high. I can't do mama's.
No, I can't do mama's yet.
Nope.
I can't either. Don't feel bad.
I can't do it. It's too hard. She's too high.
Yep.
You know, she's in the high level.
Yeah, she's at the highest level. Yeah. I'm not quite there yet either.
Are you almost there?
I think I'm just a little behind, but I'm close. I'm trying to catch her, but she's the top.
Okay. Make sure to catch up her.
Yeah, I'm gonna try. I'm gonna let you know the next time I talk to you. I'm gonna work real hard. Try to catch her.
You gotta do your homework.
You have to work really hard too.
I gotta do my homework, so I gotta go.
Okay, sounds good. Work really hard.
Okay.
Bye-bye.
That's nice.
Well, why whenever I say hi to your teacher?
Hello, guys.
Hello.
Hello.
No, why should just want to
Hey, Moses.
Leah, sorry I didn't get back to you till really late. I got off work
Okay.
really, really late. I apologize.
No, it's okay. Thank you.
So is your work still going in full form?
The part that is that my family owns a bunch of properties and I have to fix things, I guess, in all the places that go wrong over time. So I just yeah, I'm still working full time and as well as doing this. So I kind of have to, otherwise I can't afford my living.
Yeah.
But it's worth it, and it's not forever. So I just have to put up with it for now.
It's impressive. Hello, Luke. What's up with Michael? He was not there last time either. Any idea? You guys in touch?
I don't know.
Maybe he's spending.
Oh, here you go,
Here he is.
Michael. I was just asking, where is Michael? I think last time, since you were late, I thought you're not going to be here today either. So I was wondering if you're okay. Okay. So we are all of us here, right? I think Khaled is. If you noticed, I finally got around to grading the midterm one. And I think my simple advice is that I feel most of you, except actually Michael, was not comfortable with vectors. And I think Luke also, I would say Luke and so I think it's okay to take names here. What I've decided is that midterm 2 will also have a question on vector calculus. Okay, only on vector calculus, not on differential geometry, basically being able to take a curl or a gradient or a Laplacian. So those are the three things that come around, right? So only just the vector calculus part, not the differential geometry part. Is that clear what I said? Only one question on that in midterm 2. Okay, so just some grades that are there. So this is midterm 1. So the highest was 96, 92, 77, 65, 64. And the total grade based on that was, this is, how do you put this? So this was 97, 96. Around 72. And there was a curve, there was a significant amount of curve. So this is the extra credit to begin with. And just to give you a picture of these two need not match. Actually, this is 0.8. And remember the curve factor. So this time I gave back 30% of the points that you lost. So that's, usually it doesn't come out that high. And based on that, the scores are 98, 97, 83. So don't give up. My point is that, so just catch up. That's the way I would say. Even like since there are more than a few exams left, you can even go to an A from this point, even if you're on a low B. So don't give up. At the same time, this is all a time to reflect, right, as to where you stand. So, okay. And any comments from you guys? Was I reasonable or was I too harsh? Nothing. Okay. But feel free to talk to me if you want to the office hours or anything. Hopefully it was all clear. Okay, about what we do from today. Today I want to at least wrap up the first part of the analytic function, but there is a second part which is kind of pretty much the same. We try to analyze analytic functions using integrals instead of differentiation. That also has can be analyzed like that, but then instead of really going to the conceptual part of analytic functions, there is a nice application that comes out with this, and that's called contour integrals, and that has a lot of nice features which we can exploit. So I might spend a week or so on it, and then wrap up complex functions. So that's my plan, but next week, there's on Tuesday, we don't have class, so that's a small distraction there. So there is no class on October 6th. That's Tuesday. And there's an exam on Thursday. It's a little tricky. So I made the homework 5, which was due. Did you guys submit by the way today? Hopefully.
Homework 5?
Yeah. Is it all over?
I think you extended the due date for homework 5, did you not?
Yes. I did extend it, so I was not very sure when I did that. And so now it is due on October 7th. I made it, so this is the Wednesday before that exam. I didn't want to make it due on the day of the exam. So that's midterm 2. And we agreed that this is going to be in class. Did anyone check what was the status of the active cases in the campus yesterday? When I checked, it was the site was down.
I think they've changed the way that they're doing it. I'm guessing there were some complaints about how like it was a little bit confusing about if there were this many cases this week and this many cases the week later, how the numbers related. Like, did 25 people in 1 week no longer have the cases, or is it just this is how many people since the last recording have the cases? So they like updated their website to where you can see like the week of this. I think I was a little confused about.
Can you check the website? Because I couldn't reach that yesterday.
Yeah.
I tried only once. I felt it was all, like it seems to be all relatively better in our place. We have been lucky. Okay. And okay, so some questions, right? So here are some, so this is what comes to my mind on what kind of questions I'll ask on midterm 2. So there might be, again, these are tentative, but gives you a thought of what it is. Here you go.
Yeah. I guess, see, they've updated it to where they give you like week by week, and then I don't really understand some of the ways that they've done this, but I think they try to explain it. I just haven't read it. Well, it looks like there were 311 tests the past week, or I guess this was 2 weeks ago. And there were 9 positive cases, 6 students, 3 faculty.
Okay.
So it looks like the trend is good.
Yeah.
But what I was confused about is, I guess they don't have the cumulative number, or here it is actually. So I guess this is how many people since September 11th have had it. But it doesn't really say how many people have it right now. I guess this is the number of people that tested positive, but how many of this tier is also in the next one? I'm not sure.
Okay.
Yeah, I
but
think it's
still. Go ahead.
number of new positive.
Yeah, it doesn't really give like a total number of people that have
but
it. It just gives you how many new cases, I'm guessing.
Mhm.
There's a number of positive cases in this week.
Yeah.
But still, just at least some marker there. So
Hmm.
it's a reasonable marker. Yeah. Okay. So I think it seems like we will be able to have it in class. And yeah, Jordan, since you are relatively far, you have the choice to take it at home, but with a reasonable camera system, right? Which is whatever you have is good enough. Okay, I was saying what kind of questions I might ask. This is a tentative list. Think of cube roots. We talked about cube roots. Not just the cube roots of one that I discussed. Try to understand what is Cardano's formula. I don't know how far I will go into it, but the cube root that way. And then we did do one example on cube root in the class, so I'll look it up. And I'm thinking visual inspection of analyticity. That means to say that if I give you the function, then you can always check whether it is analytic or not, at least to a certain extent, using Cauchy Riemann conditions. But what if I just show you the shape of a function, right? What can you say about the analyticity? So what will you look for in a function if it is not analytic, or is it analytic? So understanding of that, maybe, of course, Cauchy Riemann conditions, right? But surely you can build something on that, and then conjugate functions, right? So conjugate functions, just looking broad, something on that, and a question on vector calculus. That's broadly what I'm thinking of. Again, these are topics, name of topics. I haven't made the exam yet, but this is how I think. Start thinking about the exam at this stage, but I haven't made any questions. Okay.
Visual inspection for analyticity. My question is, how do you answer a question like that? Is there some formulating to be done, or is it just you look at a function and determine whether or not it's an analytic function, or is it more of just a?
It is challenging, actually. That's why I'm thinking of doing that. I've never done this before. Surely, remember that isotropic derivative, right? Think of isotropic derivative. That means to say that on the xy plane, on the complex plane, you should be able to approach the function from, approach a point on which a function is defined from any direction, and it should give you the same derivative. Do you see what I'm saying? In that limiting sense. So for example, and this is too trivial an example, like this is a step function, right? You know that the derivative doesn't exist at this point because, actually derivative exists at this point, right? What is it? This one, right? So if you have a function like this, on the left-hand side, left-hand limit is -1, right-hand limit is +1. So you immediately know that this derivative is not well defined at that point. So now what we have is that this is an isotropic derivative. You can come reach this limit from all possible directions on a plane. And you want to have a visual feel for, oh, is this really having a unique derivative or not? Does that make sense? Roughly?
Yeah, So that's exactly what I was asking.
Yeah, so it might be, I want to think of functions which have a nice features like this, and maybe give you plots of two functions, and then ask you, without giving you the actual function itself, ask you, oh, is this analytic or not? Something like that. Okay, so it should be relatively simple, but it will use the idea of isotropic derivative. Okay. Today I want to do, if possible, two things. One is do another example on conjugate functions that we talked about. And actually on conjugate functions, it seems like, so this is conjugate functions. I do know that these are called conjugate functions 120 or 140 years, 150 years back. When I searched for conjugate function the other day on the internet, I was not sure whether this is what it meant. So be careful about searching for conjugate functions. Maybe you want to look for conjugate functions and then complex numbers and then electrostatics. So you want to add in a few more keywords on that. Okay. We did the simple example of f is equal to z. If you have f s equals z, right, which is x plus iy, and we had this interesting feature that you can think of it as the equipotential lines due to a planar conductor, but we are in 2 dimensions, so this is a line conductor in 2 dimensions, which is equivalent to a planar conductor in 3 dimensions, and the equipotential lines represent your u and v. And the electric field lines will be perpendicular to that, and that's your v. That's one configuration that corresponds to this. You can have another configuration. So this is a conductor, right? So this is conductor. You can have another configuration, and which gives you exactly the same thing, but in a dual form. And now the equipotential lines are this. And the electric field lines. Oh, did I say this correct? No, right? Electric field lines go down actually, because they go from the higher value to the lower value. And in this case, higher to lower is the other way. And in this case, the conductor is down here, and you set it to 0, like volt V is equal to 0. Okay, that's good. Now let's do f is equal to z squared. And in your homework, I think you do z cube or maybe even higher powers, and there is a significant pattern in there. Z squared is x plus iy, the whole square, and which is equal to x squared minus y squared. That's your u, and it is plus I times 2xy. Right, so we can identify our u and v immediately. So u is equal to x squared minus y squared, and v is equal to 2 times x times y. And immediately notice what we try to do is that you look for, in this case, we try to look for constant u's, right? What are the surfaces of constant u? So let me try to I'll draw them. You. So constant u, let's say here we started with u equal to 0. Right? So u equal to 0 implies x square minus y square is equal to 0. That means x is equal to, or y is equal to plus or minus x. Right. So that's your two lines. So let me try this out. So that seems to be your y is equal to plus x. That's y is equal to minus x. And we want to choose this to be our plates, conducting plates. So that's your u is equal to 0. Right. And that's okay. But what about u is equal to x square minus y square? Our equations say that suppose I want to plot y and x, right? So this is my x and that's my y. So my y would be equal to x square minus u. Okay. So what is that equation? How does that graph look like? Y is equal to x square minus u. Let's say, or u is equal to plus 1. Let's say. How does that plot look like? This might be a hint. So maybe this equation is more familiar. Maybe another hint. X square plus y square is equal to r square. That's it. That's a circle, correct? And so x square minus y square is? Think of a metric. I think we talked about this.
Hyperbole.
Oh yeah, hyperbole, right? It's a hyperbola. So, but then we just have to choose which hyperbola are we talking about. So if u is equal to if u is equal to, let's say, minus 1, let's say, correct? So u is equal to minus 1. So let's set u is equal to minus 1. Then this is x squared plus 1. So x is equal to 1, x equal to 0, this is somewhere here. And as you increase, that grows, so the hyperbola would look something like this. Pretty much the relativity has the same curve. So this is u is equal to 0. And that's u equal to minus 1. And you clearly see as I move forward, so this will be u equal to minus 2. What about u equal to, what are the how do I get these curves? But it's the same thing. There's a plus or minus in here, right? U is equal, or y is equal to plus or minus in here. So this is also u is equal to minus 1. So this is u is equal to minus 1. It's negative, so this is u equal to minus 2, let's say. Something like that. What if you have u is equal to +1? It is good to see this as another way. Instead of writing y, write x is equal to y square plus u, right? Plus or minus, and then you will see these plots in this sense, right? So you can see that this will be u equal to +1. That's u equal to +2. Now the same thing because it's plus or minus. That should be straightforward at this point. If you have plotting software, it's easy to see that. That's good. So what we have is U gives you your equipotential lines. Then we also said that what about the electric field? We argued that this satisfies the Laplacian. So if you have equipotential lines, if U can be thought of as an equipotential lines, then what's your associated electric field in the real two-dimensional x plus y plane, not the complex plane? So the electric field will be negative gradient of U, right? And that's the same as take the derivative of this minus I hat times derivative. So this is 2x and minus j hat plus j hat, right? Plus j hat 2y. It's a minus, but then derivative is minus 2y. So that's good, but we would like to see the electric field lines. Right, this is the electric field. If I were to ask you to plot this, you have to actually go to each point and look at what is the electric field. Instead, a good thing to plot is the electric field lines. And for that, what we said was that you have to make this proportional to a line element. ds is equal to dxi plus dyj. And then take the ratio, right? Then that gives you the equation of